Hey guys, and welcome back to another YouTube video. This is gonna be a really cool video where I'm gonna be teaching you how to build a deep fake using Python. And this is not gonna be one of those videos where I use just a pre-made API and make a bunch of calls on an image and actually get a deep fake. No, in this video, rather video series, I'm going to be teaching you how to actually go over the steps of actually creating, dealing with all of the AI related stuff and all of the neural networks to actually create a deep fake using Python. So I'm going to be doing this using Tensorflow. However, it is totally fine if you use some other framework like PyTorch. The way this code is written is that you actually won't have to change a lot of stuff if you want to change up your frameworks. All of the pre-processing steps will remain the same, which is really good. So even if you kind of are using some other framework, it is going to be totally fine. So uh, that's besides the point. Let's actually get started with this project. So I actually, as you can see, I've actually gone ahead and written up the code and this was really because of the fact that I actually spent a little bit of time writing this code because I wanted to keep it a little neat. I mean, it's still not very, it's not like exceptional code. It is, there are some areas where it is kind of untidy, but I mean, I kind of wanted to do that, so I spent a little more time with this program. So let's just get started. And first off, I want you to actually look at the deepfake architecture, and before we actually jump into the code, because I think that's a very important thing, and you really need to know how a deepfake is created under the hood, like not the math really, but what is the architecture needed to create a deepfake. So I really just found like this from some I found it from a blog post, and this image has been extracted from a paper by this person. I won't try to spell it because I'm pretty sure I'll butcher that. So this was taken from this paper, just attributing that. Alright, so as you can see, this is how the deepfake architecture works. And believe me, this is actually super simple, as you can see. So really, all you do is you take some fake, and before we even get started, a deepfake is based on the concept of autoencoders. Just an autoencoder, nothing like some variation autoencoder or nothing like that. It is not a GAN, it is just your standard autoencoder. So the way a deepfake works is you actually are trained two autoencoders. The first autoencoder, basically what it does is it takes like your face, all right, so, any face that you wanna like the face that you wanna apply to the other face. So I don't know what to call it, but yeah. So basically, you take that face and you send it up to an autoencoder. This autoencoder, and as we all know, the way an autoencoder works is it will take some higher dimensional data and it will kind of reduce the dimensions as we go, and then it will kind of produce your coding layer that we have. And these are our feature maps. So this is really going to be your coding layer. And as we all know, what a decoder does is it takes a look at your coding layer and it tries to regenerate the same input data. And so if you would pass this into your decoder 1, so this would actually be encoder 1. I don't know why they just said encoder, I'm not sure, but this should actually say encoder 1 over here. So if you pass it to your decoder 1, then it will give you back the same image that you had previously supplied it, given it, whatever I want to say. So it will just generate the picture of this woman over here. But what we really do in this case in an autoencoder is that we'll actually go ahead and uh, pass these feature maps to another decoder which has been trained on a different set of images, and now it will actually generate like some other face on top of like this body. I don't know what to call it, but whatever. So as you can see, this is how this entire architecture works. So yeah, now the cool thing is it actually isn't too complex. So it's actually relatively simple to implement, and that's good because if you will actually look it up on Google, I was struggling in some areas while I was trying to make this project, and when I actually looked it up on Google, I actually saw that there aren't many tutorials that actually, or any blog posts that actually go into the code that is required to develop an autoencoder with TensorFlow. I don't know why that is the case. I seriously don't. I mean, this is a pretty important and a great concept, but that's really the state of things. So I really had to actually figure out all of this code by myself. There were a few blog posts that actually went into the code, and those were pretty helpful. And I might just link them in the description. Remind me. There's a chance I might forget. So yeah. So now let's go into the code. Now, right now, I actually have not focused a lot on the model. It is a very simple model, so the outputs aren't good at all. uh, I am currently working on like a convolutional autoencoder. I'm trying it out, but that's gonna be like a future video. In this video, I'm really just gonna be showing you the concept and the implementation, because the model is something that even you can tinker with. It's not like it's too big of a deal uh, in terms of like learning. So as you can see over here, we are just importing the library. So as you can see, we use TensorFlow, Keras, NumPy, OS. So we're gonna need OS, and we also use pill, matplotlib, and like I'm just using like some other standard modules. So the first is to actually load in the dataset. Now if I have to show you, now the thing is the dataset that I have is actually pretty bad. It's not very nicely made. It's a very rough dataset. So that's why, that's also part of the reason as to why the outputs are very bad. I just have like a bunch of images of myself, and then I have a bunch of images of Donald Trump, because that's the only good kind of headshots that I could get. Like just the pictures of the head. I just couldn't get any good images of like other people, and like there were data sets like celebrity data sets and stuff, but it's just that those data sets were quite large, and I didn't want to go through the hassle of downloading them and like just getting the important stuff. So really I was just trying to get the code part done first, so that's why I really didn't deal with all of that hassle. Alright, so the first thing that I really did is I obviously had to load in the data. So the first thing you need to specify is the image dimensions, because the thing is that the data that I was working with, the my images, the dimensions of the image were actually very large. So what was gonna happen is that the thing is that my model would kind of have a very hard time to learn, and more than that, the like it would be able to learn eventually. That's not a big problem. The main problem would be that in my case is that the processing time would be too large, too much. So I mean, and since we obviously don't have a lot of GPUs right now, we can't exactly do that. So I mean, I really just had to clip the data to 100 by 100. I mean, you can do like 400 by 400, 256 by 256. It's up to you. I have kept it at 100 by 100. I mean, this is just something that you can play around with. Then this is the function that I use to load in the dataset. It's actually a relatively simple function. I just have like a list, and then I'm just getting all of the files. Oops. That I have in like the path. So in this case, I'm just taking path in as like a parameter, and then I'm just like looping over each of those file. And if the file ends with like a .jpg, so then I will know that it's an image and it's not some like other file. I don't know. I was having some issues where like it would get some other files, maybe something like that, and it really wasn't working very well. So I just added this line. So this will make sure it is, if it's like a JPG or not. In a way, you can make this by adding like another extension parameter over here and checking if it ends with dot extension. So in that way, like if you're dealing with a PNG, then you can kind of specify that over here. But that's up to you. And then I'm just opening up the image as a read, basically, because the thing is, if you just use image.open and specify the path, you actually cannot get the contents, like the pixel values of the image, which is what we actually want to get. And that's really important, right? Because if we have to feed in things to the data set, we can't just feed in like some image object to the data set. We actually need to feed in the pixel values to the data set. And so you actually have to specify this r parameter, which basically means that you can read the image pixels, actually like the contents. So then I'm just resizing it to the 100 by 100 dimensions. Now there might be some other sophisticated way to do that, which I think might be a bit better. I don't know. Maybe this is a really good method. I seriously don't know. This was the first method that I, you know, saw that worked. So I just ended up doing this. The next thing I'm done doing is really just getting the pixel values. All I'm doing is you just do a list get data. I'm pretty sure, because like you actually return some other data type. I don't know which one specifically, but it's not a list, so you have to convert it to like a list type. So yeah, and then I'm just appending the pixel values to the data set. And now I'm just doing the converting the data set to a numpy array, because obviously that's the data type that we're going to be working with. And then I'm just applying it to the original images, so my images and the other images. I mean, you could name this a little better. I know original images isn't exactly a good name. Like, it's a little ambiguous, so that's why, but I mean, that's the name I came up with. Alright, so then I have my original images and I'm just reshaping it. Basically, because what was happening is that when I was actually loading this in, the shape of the pixel values when you append it to the data set was the shape, like the number of images, comma, like 100 into 100, so it was like 10,000, and 3, so your color channels. So it wasn't exactly splitting the width and height into like two distinct things, which is not what we want when we are actually doing like a model. So I ended up just reshaping them to like 100 by 100 by 3, and then I did the same with the other images. Next, I just normalized the data from 0 to 1. I mean, pretty standard stuff. I don't think I need to go over this. All right. And then I was just kind of just confirming the shape of my data. Then I just kind of just checked if nothing had broken in terms of my images, so I just kind of showed them to the screen and it worked. So the next thing is I've actually gone ahead and coded up my own layers. I know that's kind of, why would I do that? But that's just something that I do as a good practice. It's a good exercise. Really, it's like, even though the dense layer that I've coded is practically the same, in fact it's kind of bad because the initializer I'm using is not very good in terms of the model that I'm building. So so even though it's not like I'm doing something crazy or something new, the reason why I'm actually coding out my own dense layer is because it kind of is good practice in a way that in the future, if I wanted to actually build some sort of a complex layer for some more complicated task, I'll at least have a good understanding of how to approach something like this. And it also familiarizes you with the syntax of the library that you are working with, and it's always just a good practice to code out your own layers. Now, I'm not saying that if you are working with like some MNIST data set, you should do all of this stuff. No, you should only do this when you are working with at least, like, if you're building some project that you like, I would recommend that you use like a custom layer that you make. I mean, it's basically the same thing. All you really do is you actually inherit from the keras layer class. So that basically gives you like most of the functionality. Like, what I mean by functionality is like all of the parameters. The only two parameters that I was really taking was the number of units, so that's like the number of neurons that you have, and the activation. So in this case, activation by default it's gonna be none, basically, because I mean it's an optional thing. If you want to pass it, you will, otherwise you won't. And then you're just passing the quarks parameter, since that's just the way Python inheritance works. And then we just call like the super, I don't know what to call this line, but the super statement, I don't know what that is. And then we just do self.units equal units, and basically what this statement does, it is that it gets the activation that is being used. The next thing that we have is the build function. The build function is really used to initialize any parameters that you want. So like, you need to initialize the weights and bias, so the build function is really used to initialize them. So in the dense case, we need our kernel and bias. Now the reason I am calling this kernel and not weights is because the thing is, if you use a term weights, you can actually get an error. That's because in some keras code, they have actually used like a self dot weights. So what actually ends up happening is you kind of conflict with that statement that's in the keras code, and so you actually will get an error. So you don't want to set like a conflicting name over here. So that's why I use the term kernel. But you can use any term over here. It's not like you have to use a specific term. That's why I actually named it as weight, so future me will actually know why. And I also just commented it over here. And this is just the shape. I mean, to be honest, I this is really just for the matrix multiplication. I mean, you use the batch input shape over here, and you just get the last element of the batch input shape, and the other part, the columns will be the self dot units. Initializer is I'm currently using Clarote normal. uh Clarote normal, it's not working with this data set. I'm pretty sure Keras uses Lika normal or some other one. I don't know what Keras uses, and to be honest, I really should go and look that up. But yeah. And then I'm just setting the bias. The bias is initialized to zeros. but I mean you can use any initializer that you want over here. All of this stuff is that something that you can play around with. I'm not gonna go over that. So these are just like hyperparameters. You can tweak them however you want. If it works, it works good. This is our bias, initializer zeros, and name is bias, and then we are just calling like the build method over here, so it kind of initializes everything. And then this is the call method. Call method really is just it's really just like the actual computations. You put them in the call method. Here I'm just performing the dot product between the inputs and the weights, and then I'm just adding my bias. So that's really just like a sum of weights and inputs and then the bias. Next, I've just coded up my own flatten layer. Uh, as you can see, I have actually gone ahead and coded like almost all layers, like for like a fully connected neural network. So I have my flatten layer over here. Flatten layer obviously doesn't take any inputs over here. You might say, well, input shape, but to be honest, I really was since I wasn't using it in my model, I really just didn't do it. This is like specific to my use case. So here I just have the call method. The call method again performs a computation, and the way I'm doing it is basically I'm performing a TF reshape at the -1. So basically what that does is it's gonna reshape your data like by taking all the dimensions and then putting them into like one dimension. But the problem was that it actually the shape of your data in that case was actually it wasn't the shape that my model needed the data in. So it was like something like it just had one shape, so it was just going to be like all of that was put together in just the first dimension, so there was no extra dimension. And when the model was actually getting my data, it was like none comma the dimension that I wanted by doing the TF reshape. So what was happening is that was kind of conflicting because none is going to be a bad size. So what I did was I just transposed the matrix that I would get, so you would add that extra dimension before it, and in that way we actually got that extra dimension which we could use in the model. If you don't understand what was happening, I mean just you need the transpose. You can't just do a TF reshape. And this was just my ReLU activation function. All I'm doing is just doing a TF math maximum between x and 0. Why does that work? Well, because if you look at the ReLU activation functions code, you will see that it's a flat line at 0 until at 0, and then it's going to be whatever value you have, so x. So you are just going to return a maximum. So if x is below 0, then it's going to return 0. But if x is above 0, then it's going to return x. You could also just write it down as like an if statement, but I'm not going to do that. I mean, this is much quicker, at least that's what I think, but whatever, I'm just using this. It's just, I think, a little better to use this. Alright, so next we are just coding out the actual model. As you can see, it's a very basic model. It's just a fully connected neural network. Again, the reason why I am actually also I can just use like my custom flatten layer over here. Now the reason why I'm using Keras layers instead of my custom layer is because I am using Glarot normal and I don't know which initializer Keras uses, and I'll need to go ahead and check that out before I change that, and I'm not gonna do that right now. I'll do that off camera. So the way the model works is I have my encoder and my decoder, which are over here separate. I mean, you should probably look at the way I've designed it, but that's pretty basic. I mean, it's like your flatten, your denses, your coding, and then like again pushing it up to the final dense over here. And here you can see why I've chosen 100 by 100, because if I would have worked with like more 1000 by 1000, I mean just imagine the number of neurons I would have in my output layer. The number of computations would have been immense, and I mean it really didn't make a big deal. I mean, I didn't need some ultra high resolution images to do the job, so it really doesn't make any sense. And I finally had just one input layer, just to kind of get that converted to like the Keras tensor format and stuff. So that's why. And now the reason why I actually put them into like the like two blocks is because of what you will see later on. For now, just you know that I have put them in two blocks because of a certain reason, which I will show you later on. Next, I just kind of created the encoder and decoders, and I've put them into a Keras model. And the input is going to be your input data, and your output is going to be your decode. So like this thing, whatever this kind of supplies. Next, now initially I was just using your custom stuff, like model. I was just doing like model compile, model fit. But I felt like I really wanted to do a little custom stuff for this. I don't know why, but I wanted to do it. So I ended up writing my own custom training loop. So all I'm doing is really just specifying my optimizer and my loss function. After that, I am just having creating a step function. So this basically steps through your gradient and stuff. All I'm doing here is I'm just taping the gradient as model gradients. I'm predicting. Note that I say training equals true over here. Getting the model loss by calling the loss, and since it's a mean squared error, you need preds and the original, because the way mean squared error works, if you don't know, is it's going to be y true minus y pred in like the squared term, and then I'm just printing out the model loss. Then I'm actually calculating the gradients based on the model loss and the trainable variables, and I'm applying the gradients to the optimizer so we can actually make the model better. And note that I decorate this function with the add_tf function. That's because if you do that, you actually get like a processing time benefit. So and it's not like it's gonna hinder your model in any way. So just you want to specify this. It's actually it's good if you're dealing with anything like gradient taping and stuff, especially if your model is gonna be big. It's gonna be like a little bit in terms of heavy in terms of computations, even if you and especially if you're going to be using like an optimizer that is kind of heavy and stuff. So I would recommend that you go ahead and you use like tf function. Next thing is just the training. Like this was a one step, not the entire training loop. So this is going to be your training loop, just for epoch and range epochs. I time each epoch and print it out. I really didn't know these formattings existed, so I just copied them from like the Tensorflow website, and then we just step over. And if the epoch is equal to epoch, we want to save it. So like after the final epoch, we want to go ahead and save the model with some name, which I will specify over here. So here I just specify the number of epochs and all of that fun stuff. So here I'm just like individually testing my two models by loading them up, just so that I could get an idea of how well they work. Really just doing some basic stuff. I mean, this isn't something too complex. And I obviously don't need to do this, but I'm still just kind of loaded them up. So whenever after I've run like my model, if I want to just quickly test them, I'll just go ahead and comment out all of this code, and I'll just kind of keep this code over here, which I will just apply on all of this stuff. So next I was just printing out the model layers. Now you will see why I actually split up my entire thing into like an encoder, decoder, and an input, and why I fed all of it as a Keras model. And this is why you will see. So if I go back to our deepfake architecture, just a second. This should take a second to load up. Why isn't this loading? All right, there we go. So if we go back to our architecture, now if you will see, then we have our model original and our other model. So we have the two models that are built on the same layers. Now the thing is, that means that we have the encoder, the original encoder, and the original decoder, right? Now the thing is, when we are actually getting the predictions, when we are actually applying the deepfakes, we don't care about the original decoder, right? We really just care about the decoder that actually does like the deepfake stuff. So that's why really what's happening is, you don't want to get the decoder portion of your model, right? You just want to get the part of your model that produces the feature maps, and then for your second model you only want to get the part that takes the features map and then decodes that part. So that's really why I split it into like these three distinct parts, so that I could actually pick which parts of the model I actually want. So that's why we have a encoder A, your decoder A. So that's going to be like your original encoder, original decoder. And it takes in 1 and 2. So this takes in your entire encoder. and this takes in your entire decoder. And if you will print out the layers, you will see that it's going to be 3 layers. It's going to be an input, encoder block, decoder block. Then you have your encoder B and your decoder B. Now another workaround, if you don't want to go ahead and do this, is that you could go ahead and define a custom layer, which is not going to be like your any layer, like you won't be doing any computations or anything, but it's going to be like a block. Now that's also something that people do. So you will create like some dense block or a CNN block, and that CNN block or dense block will contain like 5 dense layers, which is going to be your encoder. And then you'll create another block which is going to be your decoder. So when you'll actually print out the model and like the layers, it will not print out the 5 dense layers, rather it will print out the dense block or the CNN block. And so you can go ahead and make use of those things also. So it's up to you. You can choose any way that you like. Both of them are good enough. So again, but the reason why I didn't do that is because I was just not familiar with that syntax right now. I was not too familiar with that, and maybe when I actually go ahead and implement like the convolutional variation to this, I will actually do that. But for now, this is all I have done. So then I have my encoder B, which is your other layer model, the first and the first over here, and then I have a decoder B. Now the best way to really test if you have actually loaded in the correct layers, which is the very crucial thing, because if you don't load in the correct layers, there's no way you're gonna get a prediction that's actually makes sense. Is that you wanna run the encoder A and decoder A over here in the predict. So over here, if you wanna do actual deep faking, you will do an encoder and a decoder B, or a decoder A or a encoder B and decoder A. However, if you wanna just test if your model works, then you will actually just do encoder A and decoder A, and then you want to see if you actually get like a correct output without any deepfakes going on, and you actually get like your face or the other person's face correctly reconstructed, similar to what you will get over here, or probably the same. Then awesome, you're more you have loaded in the correct weights and you can just do encoder A, decoder B. If you don't get that, that means you have screwed up something over here, and you want to go ahead and check which layers belong to what. So if you have just followed along with this tutorial, then you don't need to care about that. I mean, you can upload in the correct layers. And so if you want to go ahead and customize your encoder decoder, you can just keep on adding layers over here, and you won't have to change any code over here. While if you would be using those CNN blocks, your dense blocks, you'll actually have to go ahead and change code up in your class rather than your actual sequential. Keep that stuff in mind, because that's pretty important. Alright, so then I'm just getting my predictions. Again, as I said, the predictions right now are actually pretty horrible, so I'm not gonna go over them. I'm currently in the process of improving the model, but this was just the first part. I might come up with more videos, or I will just gonna show you the predictions later on in some future video, something like that. I don't know, we'll see. So as you can see, this is a project that I have created. It is like, it is quite a bit of code for me right now, because I'm not very good at like neural nets and stuff. So for me to write this much of code, it wasn't easy, to say the least. But at least I'm pretty happy with how it turned out. And as you can see, it really shows that even though it's not initially, I expected it to be much more difficult than it actually turned out to be. So yeah, so I hope that you actually enjoyed this video, and you actually learned a lot through it, because we actually went through a lot of syntax and a lot of concepts that are actually very important in the field of neural networks. We went over how to write a custom training loop, although my training loop is pretty bad. It doesn't deal with batch sizes, which is probably the worst thing about my training loop. So my training loop actually doesn't give very good accuracy. As you can see, it's like 52%, and for my first model it was 76%. So yeah, but it could train very fast. As you can see, it didn't even take like 0.1 seconds, as you can see. But that's beside the point. So yeah, so my kind of challenge to you would be that you actually create a good model. And besides that, I mean, as you can see, it really this really showed you a lot of important stuff. I mean, uh, really, I think writing your own custom training loops, designing your own custom layers, knowing all of the syntax, knowing how to load in data, how to normalize it, how to reshape it, and how to deal with the shapes, and how to debug code, and how to see if your images are actually making sense, and loading in model layers and getting the correct layers. And these are all very foundational building block concepts that I think are very very important while doing anything in neural networks. So yeah, so I think that this entire tutorial is really useful for you guys. So I hope that you also found it useful, and I hope that you actually enjoyed this video. I'm pretty sure I'm gonna have this code up on GitHub. I don't know, I might not have the data set on GitHub, basically because one, it also has my own images, and I actually did look pretty silly in those images because I'm making all sorts of